Hydroboration-oxidation of an alkene. This is a reaction that takes an alkene and forms as a product an alcohol. If we look at this alcohol product compared to the products of an oxymercuration, demercuration, or an acid-catalyzed hydration, we can see that we have a different regiochemistry. In this reaction, the alcohol has added to the least substituted carbon atom of the alkene, and the hydrogen has added to the most substituted carbon atom of the alkene. The way that we describe this regiochemistry then is anti-Markovna. It is not following Markovnikov's rule. So recall, Markovnikov's rule would say that the hydrogen would have attached to the least substituted carbon, and then the alcohol would be on the more substituted carbon. So these are the conditions that we would want to choose if it was the least substituted alcohol that we desired as a product. Looking at these reaction conditions, we have a two-step reaction. We have borane, BH3, complex to THF. So THF is a solvent, it's a cyclic ether. And it is stabilizing that boron. So let's take a look at the mechanism for this reaction, or at least part of the mechanism for this reaction. So the boron itself is electron deficient, okay? And since it's electron deficient, right, we see we only have 6 electrons around the boron, that means that boron is electrophilic. So although we've called this reaction anti-Markovnikov because the hydrogen is not adding to the least substituted carbon, it's still following the rule that the electrophile is adding to the least substituted carbon. It's just we have a different electrophile than what we're used to seeing. So this first mechanism step is the only step that you need to know for this reaction. So the alkene is the nucleophile. It attacks the boron, which is the electrophile. And at the same time, that hydrogen is transferred to the more substituted carbon atom of the alkene. Because this is a concerted addition, that means the boron and the hydrogen are transferred to the same face of the alkene. This is known as a syn addition. This is the step that sets the stereochemistry of this reaction. So the hydrogen and the boron are on the same side. There are many more steps to this reaction that you will not be responsible for knowing. What you do need to know is that in this oxidation step, the oxygen replaces the boron exactly where it is, so that overall, the hydrogen and the alcohol that are added to the same face of the alkene. Let's look at one more example. I'm going to draw a cyclic alkene where we can see more clearly this syn addition. Okay, so I am going to start with a cyclohexene, and I'll put a methyl group on that cyclohexene so that we can see the regiochemistry. So we have a difference in the substitution. So the first step, borane in tetrahydrofuran solvent. The second step with hydrogen peroxide and aqueous sodium hydroxide is the oxidation step. Okay, so the boron and the hydrogen will add to the same side, and eventually that boron will be replaced with the oxygen. So here is what we will see. So if we've got the methyl group sticking out, the hydrogen that added to that more substituted carbon would be going back. And to show the syn addition, the alcohol product that we form will also be going back.